This video will focus on the stars and our universe. 6.2.1 is the sun as a star. If you didn't know that already, our sun is a star, a very special one to us, but there's nothing special about it compared to all those stars you see at night. In fact, it is kind of a typically medium-sized star, somewhere in the middle, not too big, not too small. This image shows you our sun relative to the planets. Our Earth is just here, so it shows it is really big compared to the planets, but compared to other stars, it's kind of in the middle. You need to know that it's made up mostly of hydrogen and helium, mostly hydrogen and some helium. And you also need to know that it emits most of its radiation in the ultraviolet, visible, and infrared. That's what this graph is showing. In fact, most of it's in the visible, and that's why we've evolved to see in the visible light, because it's the most common light source down here. But it also emits quite a lot of ultraviolet. That's what causes skin burns and so on. And the infrared is that nice warm feeling that you get when you're out in the sun. You need to know what powers our sun, what provides all that huge amount of heat energy and light energy, and it is fusion. Very different to fission. Fission you did in the last topic. That was when a larger nuclei splits into two smaller nuclei. This one is the opposite. It's two smaller nuclei. And all you need to know is that it's hydrogen. In this case, it's two isotopes of hydrogen. That's these two here. Tritium and deuterium are isotopes of hydrogen. One has an extra neutron, another one has an extra two neutrons. And these fuse together to form helium. That's where that helium in the sun comes from. But in that process, and you'll learn more about that in year 13, huge amounts of energy are produced, and that's what powers our sun. We're trying to achieve this on Earth. We haven't quite achieved it yet. You do need to know that for the exam. But that's what ITER is doing, and if they do manage to do it, it is a lot of energy and it is clean as well. There's no carbon dioxide. So we still haven't managed this. Fission we do. That's a nuclear power station. But fusion we haven't managed just yet. Returning to what we're covering today, we've now covered the sun as a star. So that's one specific star that's really important to us, obviously. Now let's look at all the many other stars that are in our universe. Now the first thing to realise is that stars are often grouped together in something called a galaxy. Now you're expected to know that a galaxy is made up of billions of stars. Our galaxy, the Milky Way, has billions of stars, and our sun is just one of many stars in there. Nothing special about it, just happens to be where we are. But the Milky Way is made up of billions of stars, and nearly all the stars you see in the night sky, if you look out tonight, are part of our Milky Way. If you've got really good eyesight or binoculars, you might see another galaxy, which is Andromeda, and that's made up of billions of other stars, but nearly everything you can see is in our Milky Way. So we're not even talking about other galaxies out there. Our sun and Earth are just some insignificant little speck on an arm of that Milky Way, orbiting around the centre of our galaxy. Now you're expected to know that the stars in our galaxy are a lot further away than the sun is to the Earth. Now this isn't even to scale. The sun to the Earth is they're extremely close. The nearest star, which is a triple star system called Alpha Centauri, the nearest star is actually Proxima Centauri, which is part of that system, is 4.1 light years away, which is over here. So our sun to Earth distance is way smaller than the distance from the sun or Earth to the nearest star. So the stars are a lot further away than you can probably even fathom. Now one way of measuring distance to stars, as I've just mentioned, is the light year. A light year is the distance travelled by light in a year. So that you need to know that definition. Light year is not a measure of time. It has year in it, but it's not a measure of time. It's the distance light travels in 1 year. Now you can do some calculations here. Distance is speed times time. And you know the speed of light in a vacuum is 3 times 10 to the 8. You know how long there is in a year. There's 365 days in a year, 24 hours, and then 60 minutes per hour and 60 seconds within that. And then you can work out how far that distance is. And as you'll see, it's quite a large distance. In fact, when you do the calculation, you get approximately 9.5 times 10 to the 15 meters. You are expected to know this, so I would just learn this. But if you're ever stuck in the exam, hopefully you can calculate it based off this, and they could get you to calculate it there, but you do need to know this. It's a number you need to remember. So if we look back at this graphic now, knowing that, what this is saying is that when we look at this star over here, Proxima Centauri, we are looking at what it was like 4 years ago, because it takes light 4 years to reach us. That tells us the distance. And it's such a vast distance that it's so slow. I mean, the sun takes 8 minutes to reach us, its light, so you're seeing that 8 minutes ago, but it's quite fascinating to think when you look at the stars in the night sky, you'll see how they were, in some cases, hundreds of thousands of years ago. Let's now have a look at the life cycle of a star. You might look up at the night sky and think those stars will always be there. In fact, over the billions of years of our universe, stars come and go, they're born and they die. Our sun is just an average star sitting about here on this life cycle. For stars of a similar mass, they follow this top pathway here. For more massive stars, I think it's about 8 times the mass of our sun, they follow this pathway down the bottom here. The key thing is they're all born in a stellar nebula, which is effectively an interstellar cloud. Now, it's called a cloud because it looks like a cloud on Earth, but it's not made up of water, although there is some water in there. It is made up of what we call dust and gas. Now, dust isn't what we have in our room, dead skin cells. That's just small molecules. They could have hydrogen, helium, carbon, and other things, depending on where they are in the universe. And you know what gas is. But most of this is hydrogen, because remember, stars burn hydrogen, that's their main fuel. Now, what you'll see is there are areas where, just because a couple of atoms bumped into each other, and then a few more atoms are pulled in, and a few more and a few more, like here, or here, or here, which are higher density. Now, these will start to attract, due to gravity, molecules from around there, until they get higher, greater and greater mass, and they start attracting more and more, and then 2 bigger ones might merge together. And over millions of years, eventually, they get such a large mass that this happens. So here you see all the dust and gas that was here has kind of come together in the middle here to form something called a protostar. Now, what is a protostar? Well, a protostar is when that gravity pulls in that interstellar cloud, it collapses, the temperature increases because gravitational energy is being converted to heat and thermal energy, causing the temperature to rise. Eventually, when that temperature gets high enough, fusion can kick in. When fusion kicks in, that star starts to become more stable because this happens. Gravity is trying to pull that star together and all that. Remember now, fusion's started, so energy is being output. It is now effectively a young star. But that fusion energy puts out a huge amount of energy, and when that balances out gravity, we reach a kind of degree of stability. This is now a stable star or main sequence star like our sun, and that's what our sun's doing right now. The high temperature in the centre is what kind of applies that outwards pressure, and that high temperature comes from fusion. It's kind of a self-fulfilling loop, because as it gets hotter, it does fusion, and fusion produces more heat, which keeps that fusion going. Reminder, we're trying to achieve that on Earth, and you can see why it's so difficult. Eventually, obviously that star is burning hydrogen. Eventually, so at this stage it's mostly hydrogen, it will run out. And when it runs out of hydrogen and is now mostly helium, it becomes a red giant. If it's a more massive star, it becomes a red supergiant. Now these are big, the name giant is correct here. Our sun, when it dies or becomes a red giant, it will expand to the size of the orbit of Earth approximately, swallowing Mars. We probably won't be around then. And it kind of, as it does that, it throws out sort of dust and gas and new and elements from that star that formed as hydrogen's fused to helium, and helium also fuses further up to things like lithium. It throws those out. What it forms is something called a planetary nebula. Now this name's a bit annoying. It's got nothing to do with planets. Planets aren't born from it. It's just a name. It's a bit of a misnomer. So kind of ignore the planetary bit. Just learn that it's a planetary nebula. Now this is kind of dust and gas that's thrown off from that star, expanding, contracting, expanding, contracting. That centre of that planetary nebula, little white thing there, is called a white dwarf, and it's kind of what remains of our star. It will slowly radiate away its energy till it cools and becomes less white, and goes from there. I wanted to show you a planetary nebula since they're so good, so I just found this on the internet. Here's a planetary nebula. Again, nothing to do with planets. You can see the white dwarf in the centre there, and this is kind of all dust and gas that's been shed off. When it becomes a red giant, that star, it kind of it kind of contracts and expands. Sometimes a bit of fusion gets going again, and it produces all these elements that are kind of thrown off to enrich our galaxy. So here's a beautiful example of a planetary nebula. Now, that was a bit big. Now back to our life cycle. Let's focus on now what happens to the red supergiant of the more massive stars. These can undergo a huge explosion called a supernova. Supernova are really interesting because after the supernova, such a huge amount of energy that we can fuse together elements heavier than iron. So anything beyond iron on the periodic table, like uranium and stuff like that, we know were formed in a supernova, a star that died somewhere in our vicinity over the course of our universe, 13 billion years. Because otherwise you wouldn't have uranium on Earth. We'd only have up to iron. You need the huge amounts of energy in here, these huge explosions, and sometimes these explosions are so bright. There's a good Veritasium video which talks about what would happen if it was near us, but they've been reported by Chinese astronomers many years ago, so bright that you can see them during the day. What they leave behind is either a neutron star, which is a star made up of neutrons, incredibly dense, because neutrons can sit kind of very close to each other because they've got no charge, or a black hole, and you've probably heard of one of those. If not, you can Google it. The interesting thing about a supernova, though, is all that dust and gas that it throws off, plus all those new elements like uranium, can then go on to form new stars. And those new stars and planets around those stars, like our Earth, will have those elements in there thanks to that supernova. So we know our sun was in a first-generation star, because when that supernova happens, it's all this dust and gas that we talked about back here is created. If it's after a supernova, it will also have elements like uranium and anything more heavier than iron will be found. So just like our Earth. So we know our sun was formed from one of these remnants of a supernova, that nebula, which is just a big bunch, a cloud of dust and gas. So lots of terms there. Really what you need to focus on is this. This takes you through the different steps, and you are expected to know that in a bit of detail about each one. The final part, our universe. The universe has been around for over 13 billion years. Our sun and Earth have only been around for about 4 billion years, so a lot longer than that. Now, our Milky Way, that we talked about earlier, which is over here, you need to know its approximate size, and that's 100,000 light years. We talked about what a light year is. So we know that it will take 100,000 years for light to get from one side to the other. That's why when I said you're looking at most our stars are in our Milky Way, so you're looking back in time for those. Our Milky Way is not just made up of our universe is not just made up of our Milky Way. It's made up of many, many billions of galaxies. Now, this amazing image is called the Deep Field from the Hubble telescope. And what it did was it looked at a small patch of the night sky which didn't have any visible stars in it, and they left the Hubble telescope on a long exposure, so taking in all the light it can get. And when they looked at the image, they were amazed to just see how many galaxies, just like our Milky Way, so made up of billions of stars there are. So this is a tiny patch of the night sky. I'll show you how small it is in a second. And all of these things you see are galaxies, and those galaxies have billions of stars in them. So it shows how vast our universe is. Just to show you how small that area covered was, you can read that at the bottom. So the area of the sky observed by the Hubble ultra-deep field view is compared to the area as if you looked through a straw, an 8-foot soda straw. So imagine that's a couple of meters. That area that you're looking at had all those many thousands of galaxies in. So there's lots of galaxies and stars out there. Now you might ask, how do we know that our galaxy had a beginning? Our universe had a beginning. I said it was 13 billion years old at least. How do we know that? We know that by looking at some of the galaxies in our universe. and some stars as well. And here's just some picked out from that ultra deep field. And you can see they've been numbered and shown in more detail on the right. And what you'll notice, first of all, is that their colour is very red. This is due to something called redshift. Now, the reason why they're red is because they are moving away from us at a really fast rate. We know that galaxies emit visible light. That's how we see them. And as they move away from us, if they're moving really quick, you see that wavelength of that light is going to get stretched. So if it was originally kind of in the middle of the visible spectrum, it's going to be stretched more towards the red end with a longer wavelength. Red light has a longer wavelength. That's if they're moving away from us. If they're moving towards us, then we'd see them bluer. The thing is, though, when you look at nearly every single galaxy, except for our nearest one, Andromeda, we see that they are redshifted, so they're moving away from us at really fast rates. If you compare that to a light source on Earth, you know, if you have a light, you're looking up at your light in your room, that's not moving away from you, that isn't redshifted or blue shifted. But when we look at those galaxies, we see them as redshifted. So that tells us they're moving away and they're receding from us. Now the thing is, if all those galaxies are moving away from us, kind of see it there, they're all moving away from us, and you plot back, that suggests that they must have all come from the same point. Now, some people say, well, isn't that, hang on, if they're all going away from us, surely we are that point that the universe started, which is quite special, but we're not at all. If you were on another star, on another planet around another star and another galaxy, looking at our Milky Way, you will also see that moving away from them. A nice analogy is if you put raisins in some bread and then put the bread in the oven, it would expand. So all the raisins would start moving further apart from each other. And if you were sat on this raisin here, you'd think, oh, they're all moving away from me. But likewise, this raisin here, they'd all be moving away, including that one, from it. So that's the evidence that our universe is expanding. Reverse time, we get the age roughly of the universe, and it suggests a Big Bang as the origin, because all the matter and all the stars would be in one place at one point, so it must have started at some point. So that's the evidence for the Big Bang, and it comes from that red shift of the stars and galaxies that we look at in our universe. The final part covers some cosmology. Now again, there's lots of no things here. Now the first thing you need to know is that when we observe our universe, microwave radiation is observed at all points in the space around us. We call that the cosmic microwave background radiation, CMBR. It looks something like this. Anything above all those colours there show that there is microwave at all parts of our universe. Some have more than others, but the difference is very small, and it's emitted from everywhere. Now, how was that formed? Well, after the Big Bang, there's a little delay, but we don't want to go into that into too much detail, but at some point after the Big Bang, there was a huge amount of electromagnetic radiation emitted at very high energies, with very short wavelengths, because there was a huge amount of energy in the Big Bang. But as the universe has expanded, the fabric of our universe has expanded. Imagine getting a bit of plastic from our balloon and drawing a short wave on it and then pulling the balloon apart. That will cause this wavelength to get longer. So where we are now, 13 to 14 billion years later, we can see that wavelength has been stretched, and it actually happens to be at the moment in the microwave region. So that's why we're seeing all this microwave around, and it's evidence for that Big Bang at the start and the expanding universe more so. In the future, it will eventually keep expanding until we have radio waves, but at the moment it is microwaves. Now, earlier I said that redshift showed that the galaxy stars are moving away from us, but how do we know how fast they're moving? Well, if we take the change in wavelength, so what we do is we look at spectrum, which we'll talk more about next year, but these are distinct black lines that appear at certain wavelengths in a lab, not moving away from us. We get these reference values. Then when we look at objects moving away, you can see those same dark lines, but they've been shifted towards the red end of the spectrum. So they're moving this way, i.e. the red shift. That's why it's called that. Now, the more they move, so you can see the top one, the very distant one, has moved the most. Its wavelength has had the greatest change, means that it's going the fastest. So the more change in wavelength, the faster that object is moving away from us if it's redshifted. So we know that these very distant galaxies are moving faster than nearby galaxies. Another question you might ask, how do you know the distance to objects? So when I say they're very far away, how do I know that? There's many ways we can do it, but the one that you need to know is that we can use supernova to find the distance. Just need to know that what it is actually how the brightness of the supernova changes after it explodes can tell us the distance, but you just got to know that supernova brightness can tell us the distance to galaxies. You might say, well, hang on, that doesn't make sense because a supernova is an individual star, but if we take a galaxy and we find a supernova in that galaxy, and that's enough information to tell us the rough distance to the whole galaxy. Now, you might say, well, there to there is actually still a big distance, but relative to the distance from us, which is often hundreds of thousands and thousands, no, even more than that, sorry, millions of light years away, it's insignificant. So once you've got one supernova in a galaxy, and if you observe it as it goes through its explosion, look at its brightness, you can find the distance to that whole galaxy approximately. Now getting towards the final part, which is the Hubble constant. Now what happens if we plot the distance to these galaxies that we're looking at against their speed that they're moving away, their velocity that they're moving away from us? So you can see the distance from us on Earth to those galaxies, and here's their speed away from us. Now what you see is there's definitely some sort of link between the two. The further away something is, the faster it's moving. And this kind of fits in with that bread analogy we talked about earlier. Now this leads to a constant, which in this case is a gradient, but you need to know the equation. You could do it for an individual galaxy or star, but overall but probably more on this graph than drawing a straight line and then taking the gradient, you can get a more accurate value. But the H0 is called the Hubble constant. So H0 is the Hubble constant. And it can be found by the ratio of the speed at which the galaxy is moving away from us to the distance from us on Earth. So that's this equation here that you need to know. You also need to know the approximate value for H0 today. Again, just one to learn. It's 2.2 times 10 to the minus 18 per second, or seconds to the minus 1. And that number is refined as we get more and more data, but that's the current best estimate of that. They might say, why is that number important? But it probably gives us the most important thing, number in our universe, is the age of the universe. Think about it like this. Time is equal to distance over velocity or speed. It comes from just speed equals distance over time, or velocity equals displacement over time equation. So if we flip this d over v, this is v over d over here, you can see that this is equal to 1 over h0. So if you want to find the age of our universe, you can do 1 over that number that we just said is our best estimate from all the astronomers around the world. If we do that over that, we'll get the age of the universe in seconds. Of course, then you can convert it to years quite simply. Now, the fact that there is an age tells us that there is some evidence that all this matter was at some single point, that the universe was started or born at a single point. And that also comes from the evidence that we talked about earlier, that if we kind of plot back all those stars, they must have come from a single approximate point. And that's the evidence for the Big Bang. That's all you need to know for this part of the topic. Obviously, lots of no stuff. I've gone into a bit more detail. The key thing is check the syllabus. When it says no or define, you've just got to learn that.